Warning. The demonstrations you are about to see will be performed by trained and certified adult chemists. Do not try anything you are about to see at home. Normal people use tiny wax candles to celebrate their birthdays. But we're chemists, so we're gonna fill up a cardboard tube with hydrogen gas and set it on fire.
Will everyone sing happy birthday?
Happy birthday to you. Happy birthday to you. Happy birthday. It has to be helium, right? Yeah. You guys ready? Let's see if you're right. Helium is used to fill birthday balloons because it is an inert gas, meaning it is non-reactive. So if helium is non-reactive, then why did those balloons in the video explode when we put fire near them? Is there any element that is lighter than helium? Yep, hydrogen. Hydrogen is also extremely flammable, as you saw. So you can see why it would be a bad idea to use hydrogen gas in balloons at birthday parties, especially with all those candles around.
So we have here a special chemical. It is known as a super soaker chemical. It is technically called sodium polyacrylate, but basically it is a super soaker chemical, and it can absorb 1,000 times its own mass in water. And just to prove it, I have already pre-measured about 3 grams of the stuff and placed it in this beaker. And in this graduated cylinder, I have measured 297 milliliters of water. So if you do your percent composition, we now have 297 grams of water, and the total mass here is 300 grams. So this is now, if you do the math, 99% water, which is kind of cool because I could take this and place it directly over. Give it a poke. What's it feel like?
Ooh, it feels like jelly.
Feels like jelly, yes. You know what it feels like? It feels like a baby's diaper after the baby has wet the diaper.
Well, I've never stuck my hand in that, so...
No, but if you feel the outside of the diaper, you're like, oh, something's mushy. That's the mushy stuff.
We're gonna try to see if I can crush this can. So I'm having a hard time crushing it this way, so I'm going to crush it with chemistry. That liquid I just poured into the container is ethanol. Ethanol is an alcohol, much like the rubbing alcohol that you use at home for first aid. This liquid is very flammable, and what I am doing is moving it around so that I can turn that flammable liquid into a flammable gas. Okay. Look how strong this really is when she has chemistry.
And it's back.
Have you ever wondered how much energy is actually in a gummy bear?
The nutrition label says there's 33 calories in one piece.
But what does that even mean?
Let's use this combustion reaction to see.
First, we decomposed potassium chlorate to create a surplus of oxygen.
Yeah, it's boiling, yeah.
Then we dropped our victim in, who quickly releases all the energy held inside him in a very exothermic reaction. Whoa, that's a lot of energy. Enough for the average person to cycle 2 minutes, or walk for 4 minutes, or sit in class for 10.
Should I drop another one in there once that one's done? Can you do another one? Let's see.
Today, I'm going to be making toothpaste for my pet elephant. Couple of drops of dish soap for some cleaning action. Okay, maybe more than a few drops. Her breath is really stinky. Some food coloring, because my elephant's a little princess. And I'll be using hydrogen peroxide, which slowly decomposes on its own into hydrogen and oxygen. However, I'll speed that reaction up with this catalyst, potassium iodide. And voila! Elephant-sized toothpaste.
Have you ever wondered how fireworks are made? So what we're going to do is we're going to take that sodium chloride and we're going to dissolve it in a solvent. In this case, we'll be using methanol. So once the ionic compound is put into the solution, the ions dissociate. So we are going to be focusing on the sodium ion here, for example. Here we have the sodium ion in the ground state, and we are going to add energy in the form of heat in order to excite one of the electrons. So after absorbing the energy, one of the electrons is excited, right? It moves from a lower energy level up to a higher energy level. But if you've ever eaten too much candy and maybe had a sugar rush, you know that that doesn't last for very long. So, the excited electron is going to release its energy as it falls back down to the ground state, and it releases that energy in the form of light. Each element produces a different color due to the different wavelengths of light that each one emits.
So let's see what happens when we excite barium ions. Our second salt will be copper chloride, so we have copper ions dissolved in methanol. The third salt is lithium chloride in methanol, so we have lithium ions. This is a potassium salt, so potassium ions. Our fifth salt will be sodium chloride, so sodium ions in methanol. Our last one will be strontium ions, so strontium ions in methanol.
Now we're going to get to see those firework colors in action. So in order to make fireworks, we need to add heat to the ions so that the electrons can absorb energy. But first, I have to take my liquid, my methanol, and I need to add heat to that in order to turn it from a liquid to a gas, right? And how am I going to add heat to it? Armpits! When enough vapor has been produced, the excess liquid is removed using a paper towel, and the bottle is placed onto a cork that is fitted with a piezo lighter. The spark created by the piezo igniter will ignite the vapor inside the bottle, and At the bottom of my cannon, I have calcium carbide. Calcium carbide was used in miner lamps, so when you go down into a coal mine and you're digging, you need light to be able to see. So what they had was this tiny little dish of calcium carbide and a little tiny water drip. So it would drip, make a gas, drip, make a gas. And the gas that it's producing is acetylene gas, which is super flammable. So this worked out for the miners some of the time to make a little gas, but what happens when you make a lot of gas? So here you can see I am adding some water to the bottom of the cannon where I have my calcium carbide, and I'm shaking it up to make my gas. Everyone parts. I smell it. You ready? So if you were a miner in a coal mine, I'm sure you wouldn't want that happening on your head. And guess what? It's also a great way to carve jack-o'-lanterns. If you've ever used a glow stick, you know that you need to crack it in order for it to glow. Here I have 3 glow sticks, and if you can see, there is something inside of the liquid in the glow stick. This little container inside of the glow stick is filled with a different chemical than the liquid you see. So when I crack the glow stick, the liquid inside of the container will mix with the liquid inside of the glow stick. Alright, so as you guys can see, it's pretty dark in here. And I have some DMSO, dimethyl sulfoxide, and here I have sodium hydroxide and luminol. So let's see what happens when I add them together. Oh! Ooh. Ah. It's pretty cool, huh? For this next demonstration, we will be using dry ice. You might be familiar with dry ice from fog machines or perhaps making ice cream. And dry ice is solid CO2. We're also going to be using magnesium, which you may be familiar with from sparklers. So what we are going to do is we are going to take a block of dry ice, put some magnesium in there, and light it up. Why, though? So, magnesium and oxygen really want to be together, because when they combine, they form the very stable ionic compound magnesium oxide using this equation. So we're going to take magnesium, add it with the carbon dioxide, and let's see what happens.
And we're going to say okay, I'm going to try to cover this up, trying to put out the fire.
So let's think about the number of moles of carbon dioxide in that block of dry ice and the amount of magnesium we were able to fit inside. There is way more carbon dioxide than there is magnesium, making magnesium the limiting reagent. This means that the reaction will stop once all the magnesium has reacted to form magnesium oxide. So the funny thing about carbon dioxide, what the dry ice was made of, is that it's actually used in fire extinguishers to extinguish fires. So why was it able to help the magnesium burn? And again, that brings us back to magnesium and oxygen's love of each other. So magnesium wants to be with oxygen so badly that it steals it away from the carbon dioxide in order to form magnesium oxide and carbon, which looks like this. Okay, and if you move it a little bit, you can see the black is carbon and the gray is magnesium oxide. Do you think you would be able to squeeze this egg into that flask without breaking it? Or even pushing it? I know I can.
Oh, that's cool. What you doing? Is it gonna explode? Really? That fast? Woo!
Hey!
Woo!
Hey! Now you may be wondering, how does the egg get out of the flask without breaking? Well, it doesn't. Just kidding. Of course we can get it out. You could do anything with chemistry. So what we're going to do is flip the bottle over so that a seal is formed around the edge of the flask, then heat the molecules inside so that the pressure increases and the egg is pushed out.
One, two, three, go. Oh, yes! Yes! Oh, yes! Oh!
Wait a second. If they were all poured at the same time, then why did they change colors at different times? So this has to do with the concentration of each solution. The solution on the left is the most concentrated, which is why it happens the quickest, and the last one to change is the least concentrated. This shows us that the concentration of a solution has an effect on the rate of the reaction.